So today we're going to talk about Gossipsub, which is, I'm really happy about that because it has been a really great effort and collaboration between the libp2p team and members of the ResNet lab, myself included. In case you don't know what ResNet lab is, you should go check it out because you really miss a lot of things, a lot of interesting things taking place there. We designed Gossipsub for it to be a secure message propagation protocol for the Filecoin blockchain, and of course, not only. So what happens is that, every blockchain needs a message propagation protocol. And this propagation protocol normally would would send around messages, transaction messages, and block messages. So it's a PubSub protocol, as the name suggests, but it has to deal with some challenges that have not been dealt with in previous PubSub protocols or peer-to-peer overlays. So when we're dealing with permissionless blockchain networks, such as the Filecoin one or others, Ethereum or Bitcoin, we have several features of those networks that we need to take into account. So the permissionless blockchains, for example, are open for everyone, for anyone to join. There is no access control, which makes it really easy for malicious nodes to just join the network and try to disrupt the operation of the network. So a protocol, a message propagation protocol, what it has to do is basically avoid network fragmentation or forks, because this is a really bad thing to happen, because the nodes are not able to reach consensus and they cannot have a common view of the network. They need to do verification of messages. So as messages are propagating around, they carry together cryptographic proofs, and this enables miners to verify that some transaction is coming from the person that it claims to be coming. And of course, it needs to keep the chain in sync. So, in order to reach consensus, everyone in the network needs to have the same view of, the latest messages that are going around. So that's the main requirements that a general PubSub or message propagation protocol has got for permissionless blockchain networks. Now, there are several other things depending and deadlines depending on the blockchain that runs underneath. For Filecoin, there is a deadline which says that within 6 seconds of a message being produced, being created, it has to reach all the nodes in the network. As you probably know, the Filecoin blockchain operates based on tipsets and not blocks. So tipsets are groups of up to 5 blocks. And this is what miners are mining on. They're mining based on tipsets. So within 6 seconds, so I should mention also that an epoch is equal to 30 seconds. What this means is that we have from 0 to 30 seconds is the epoch when new blocks and tipsets are going to be produced. And we've got a 6-second deadline to propagate the newly published messages and blocks to all the nodes in the network. This is needed because the rest of the time, the rest of the 24 seconds is used in order to do all the cryptographic operations in the that are needed, put the blocks together, produce the tipsets, and go to the next round. So what we need to remember out of that is that the 6-second deadline is a really important thing, at least for Filecoin and Gossipsub. And what we try to do is we try to see, okay, it's an open permissionless network, so what could happen, what could go wrong? And we try to approach all the primitive attacks that exist in, current and previous blockchain networks. And what we, okay, can go back. Yeah, we have a range of attacks. These are the Eclipse attack, which is well-known attack, a Sybil attack, which comes first of all, someone would need to create basically Sybil identities, like fake identities, so that they have many nodes in the network. And then you can carry out a number of attacks. So Eclipse attack is one of them, where a node is basically syncing messages and not propagating messages of one node or all of the nodes in the network. We can have censorship attacks, and we can have more sophisticated attacks, which are the last two of the ones that I have shown just before, the cold boot attack and the covert flash attack. These are very interesting and very difficult attacks to mitigate. So what we did was we started designing Gossipsub, and on the way there we tried to put mitigation strategies that would help us basically recover from those attacks or stop them from the onset. If we want to describe the design of Gossipsub in a nutshell, we would say that it has got these four basic components. It's got a mesh construction, gossip dissemination algorithm, a scoring function, and some mitigation strategies, which we're going to see very briefly, pretty much all of them. Let's start from the mesh construction. So what Gossipsub has as the main principle is a mesh network. So nodes are connected to each other. No node is connected to everyone else. There is a limit to how many nodes some peer can connect to. And every node has its own view of the network. So in this figure, for example, we can see, the big kind of cloud is the whole mesh. And then every node, let's say node A in this case, has got its own local view of the cloud, which is those, how many, 1, 2, 3, 4, 5 peers that it is connected to. So this is the view, the local, in a sense, the local mesh of node A, or more accurately, the view of the mesh from node A. These are the immediate peers that node A communicates with. Now, those peers, whenever A is producing or receiving some message, what it does is that it replicates, it broadcasts the message to those immediately connected peers. So this way we can see that, little kind of smaller meshes of each node, they are interconnected with each other. And, how tight and well connected the mesh is basically depends on this D factor, the degree of the node, which is how many other peers each node should connect to. We're going to talk about how we set this D, but for now, let's keep this important part. Now, apart from that, what we also have is gossip connections, which is these dashed lines. What these do is, apart from a node receiving or sending messages to its immediate peers, it also sends gossip messages every now and then on every heartbeat, as we're going to see. What this gives us is basically further reachability to a wider number of nodes in the network. And this is good, of course, if a node is eclipsed, for example, it can send out messages through the gossip channels, not only through its immediate mesh. So a node that is joining the network, what it does is that, apart from getting an initial list of nodes, it sends graphed messages. We have two main, well, we've got more, but the main ones are the graphed message and the prune message. How these work is that when a node wants to connect to an extra node, so if A wants to increase D from 5 to 6, it's going to send a graphed message, say, to this other gray node here. When node A realizes that it has got a lot of connections at this point in time, then what it's going to do is basically it's going to start pruning connections. It's going to start cutting down connections. Of course, we understand that the more someone grafts, the more messages and the more traffic is going to create to the rest of the network. So when we're grafting, we have a range of peers where we say that this is an acceptable number of peers that we're connected to, and if we are within this range of nodes, then we're okay, which is this case actually. If someone is connected to less than this acceptable number of nodes, then it needs to graft more nodes so that it comes within the region that is acceptable. So D cannot really be a fixed number all the time. It's going to have nodes coming and going, so it's going to have to regraft to try and find other nodes. On the opposite side, when a node finds out that it is connected to too many nodes, which goes above the acceptable number of connections that these nodes should keep alive, then it needs to prune down in order to go back to the ideal range. So how these grafting and pruning happens with the heartbeat message, which, at the end of every heartbeat period, which is right now set to 1 second. So every 1 second, each node is checking how many connections it has got open with other peers. And if it's too many, it's pruning down some connections. If it's too little, it's grafting more nodes. Now, that's more graphically how it works. There is a range. We set the D. As we said, the D factor, the degree of a node, is how well the mesh is connected. And of course, the better connected the mesh is, the more messages the more traffic it propagates to the network. Now, if we link that to the security properties of the protocol, we see that, if a Sybil node, for example, wants to start connecting and tries to eclipse a node, what it's going to do is going to join the network and start sending graft requests to a node so that all of the connections within that a node maintains, so this D factor, are basically dominated by the malicious node. So the more connections, the more we increase this D, the more difficult we make it for Sybil nodes to come and dominate all of the connections, right? And the smaller number of nodes that we have as the ideal degree of the node, what we achieve basically is that we have less traffic in the network in general, but we make it easier for Sybil nodes to come and dominate all of our connections. So gossip dissemination, as I said, is basically a complementary approach to the mesh and all the messages that go around through the mesh. What happens is that on every heartbeat, the node is sending gossip messages out. So gossip messages are not sent to everyone else that the node has heard about. A node is, apart from the direct mesh connections, it has got a list of nodes that it has seen or interacted with in the past. So out of those nodes, the protocol is picking as a fixed percentage, and it's disseminating gossip messages to those nodes. The gossip messages, basically, there are two types of messages there: the I have message and the I want message. A node that is disseminating the gossip, it says, I have those messages, and the nodes that are receiving this gossip message are checking whether they also have received the list of messages that this I have message indicates. If it finds that it doesn't have some of the messages, means that these messages have not propagated to this peer yet. So what it does then is it goes back to the node that it just received the gossip from and says, I want this message because I have not heard about it. And in order for everyone to be in sync, we all have to have all messages. So please send me this, the full of this message. We have Gossipsub right now operates 3 rounds of gossip, and there is a gossip factor, which basically what it does is that is this percentage that I mentioned, that every node is not picking a fixed number of other peers to disseminate gossip to, but what it does is it's picking a percentage, and that has been done on purpose because setting this to a threshold, which right now is 25%, if I'm not mistaken, and having 3 rounds of gossip and basically every time picking a different 25% of nodes, we reach a specific probability that we are happy with, which says that, you know, if you have 3 rounds and you pick this gossip factor, then up to this amount of nodes, up to this number of nodes is going to hear about the messages that you're disseminating through gossip. So all this is tunable, and it needs to be the right number of nodes according to the implementation that we want. Obviously, as I said, you know, if we put on a graph the mesh degree and the dissemination through gossip, we can arrive at interesting trade-offs. So if we increase the mesh degree a lot and we keep the dissemination factor, the gossip dissemination factor a lot, then what we have is basically we go to an eager push approach. The eager push approach, what it does, what it points to is that because we said that every node is broadcasting immediately all the messages that it knows about, it's eagerly pushing messages out, and this creates more traffic. We have reduced propagation latency in this case, because, you know, everyone is getting to hear more messages quicker. But on the other hand, we have increased bandwidth requirement. On the other hand, if we keep the mesh degree to a small value and we increase the dissemination through gossip messages, what we do is we go to this other kind of extreme, which is the lazy pool approach. Everything is happening through the lazy pool approach, which says, you know, I'm not going to eagerly push stuff. I'm just going to wait and hear from others what are the messages that are known to the network, and I'm going to lazily ask them to send them to me. In this case, we have less traffic in the network and less traffic redundancy, of course, but the propagation latency increases considerably. So there is a trade-off there that we need to hit, and this has to do with the network design, the number of nodes in the network, what is the deadline. In the Filecoin case, we said it's 6 seconds, so, you know, you can play around with this. If the figure was not 6 but 26 seconds, then we could go towards more lazy pooling, which would reduce traffic redundancy, but would increase latency a little bit. So here is just a snapshot of a very interesting simulation that Vyzo has done in the past, where it shows, you know, this is basically when the left-hand side is when we flood the network. So we can imagine that D is very high, which means that we have kind of faster dissemination, but more traffic. And on this left-hand side, we have Gossipsub that does not have as big bandwidth requirements, but the latency could be a little bit more than the flooding approach. So it's all about a trade-off. Now, let's go to the scoring function, which is used by every peer in the network is keeping a score for every other peer that it is connected to or it has seen in the network in the past. So this score function is important to highlight that the score that I am keeping for all the other nodes that I know in the network is not shared with anyone else. So I'm not sharing this. It's not like a reputation system, which is very well known from other systems and from research papers, because that has got a different set of problems. Building a correct reputation system, it's pretty difficult. So what we said was that every node is going to keep a score for every other peer it is connected to. This score is kept locally, and the final goal of the score is that if I see a node that is scoring very highly, then I will keep connected. I will keep being connected to this node. I'm not going to prune this node. If I see that a node has got low score, I'm going to, in the next heartbeat, I'm going to prune this node because I see that it's misbehaving in a way, and therefore I don't want to be connected to this node because it's perhaps a malicious node. So progressively, if we set the scoring function correctly, what we achieve with this kind of score function and this construction is that eventually the malicious nodes will be excluded from the network, because every node who is monitoring every other node is going to kick the malicious nodes out because their score is going down. So let's see very briefly what the score function consists of. So it's basically, as I'm going to show in the next slide, is a weighted sum. So the more a node is behaving correctly, the more it improves this weighted sum, and the opposite. So it's a weighted sum of factors, and these are those that are shown here. So we have first message deliveries. So a node is incentivized to send messages as quickly as possible to other nodes and disseminate to other nodes, because this way it's increasing its score. We have a message delivery rate, where we monitor how many messages we're receiving from other nodes, and if this is within some known limit that the peer has seen in the past, then this means that basically the other node is not hiding messages, is not dropping messages off when it's receiving and tries to eclipse my node. There is message validity. If I receive a message and I see that, I try to do all the cryptographic proof, like all the check all the signatures and everything behind it, and I see that it's not a valid message, perhaps even because it's in the wrong topic, it talks about a topic that is not known to the network, then this counts as an invalid message and is dropped, and the peer that has sent this message is penalized with less score. We have the uptime. So for how long have we been seeing this node around? Because the more a node is staying in the network, it means that it's unlikely, or at least the probability of it being a malicious node is going down. Normally, what a malicious node would do would join the network and attack the network straight away. And finally, we have the collocation factor, which is monitoring basically the IP addresses from where other nodes are connecting. What we want to achieve is that we don't want many Sybil identities that come from a virtual environment, perhaps, connecting through the same connection and trying, creating many identities and attacking the network from a single host. So that's very common in Sybil attacks. So if we see this collocation factor going, if we see a node that is collocated with many other nodes, then, we score this peer negatively. This is what it looks like. The score function is a weighted sum. Of course, every different, it's very interesting to see how each one of those factors is behaving over time. Yeah, and as I said, it's a weighted factor. It's a weighted sum. Now, finally, let's go to the mitigation strategies, which right now, I mean, okay, these are perhaps examples. There are a few more, but these are the most are the ones with the most impact. We have controlled mesh maintenance, as we call it. And this is nothing different from basically getting the score function of the peers that I am connected to in my local mesh and seeing which ones perform the best. And what I do is, upon every heartbeat, I'm pruning those with negative score or those that are not performing very well. They've got a very low score value. And I keep being connected with the nodes that keep the best value, that maintain a good score value. We have then flat publishing, which is the second mitigation strategy, is a very important one, and says that when a node first publishes a message, it basically is not sending it only to its immediate mesh that I said a few slides ago, but it's sending it to everyone. And this, as clearly one can understand, is to basically avoid Eclipse attacks. So if I am connected, if a Sybil has managed to dominate all my mesh connections, then if I try to broadcast a message to my immediate mesh, I'm going to be eclipsed because all of them are Sybil nodes, and they're not going to forward the message further. If we have flat publishing, then I kind of bypass the mesh of the Sybils and I send the message to everyone that I know of. These nodes then, they do not reflood the message. They follow the normal protocol operation, and they only send it to their own meshes. We have adaptive gossip dissemination, which is, as I described beforehand, this is based on two main factors. One is the gossip factor and the percentage that a node is sending gossip to. And secondly is the number of rounds. So the adaptive gossip dissemination is targeting the first, so the gossip factor. As I said, in the current Gossipsub, I think it's 25%. So every node is picking 25% of nodes. Now, basically, multiplying the 25% or the remaining 75% times 3, we see that the majority of the nodes in the network are going to hear about some message. And finally, there is the back off on prune. Oh, only 3 minutes, okay. There is the back off on prune, which means that if I prune some other node, then I'm not going to accept this node again for some set amount of time. So this is basically saying that a Sybil node that is going to start grafting and trying to connect to many nodes, once it is pruned from some node because of the negative score value, for example, is not going to be accepted again. So we used Testground, and we carried out a huge campaign of testing on AWS. We compared the protocol Gossipsub with Bitcoin and with Ethereum. Now, Bitcoin is keeping 133 connections in total, inbound and outbound, and Ethereum is using I should mention that Bitcoin is using a flooding protocol that is propagating messages to all of those connections, and therefore it's on the side that introduces lots of traffic to the network. On the other hand, Ethereum is using a propagation protocol that is, Ethereum 1 is using a propagation protocol that is forwarding messages to the square root of the number of nodes in the network. So in this case, we set it to 33. That's the square root of the number of nodes. What we wanted, of course, is to propagate the messages to all nodes before in less than 6 seconds and achieve 0% packet loss. We use Testground, which others have talked about Testground here before. Let me go very quickly through a couple of results only. So this is the network-wide Eclipse attack, where we have a very big number of nodes. I think the ratio is 20 Sybil nodes to 1 honest node. And they're joining the network and they're trying to eclipse it. So what we see is here that the Ethereum and Bitcoin protocols, even with the publishing, they are severely affected, and it takes up to 11 seconds to Ethereum to propagate those messages, and up to 4+ seconds to Bitcoin to propagate the messages. On the other hand, Gossipsub is staying really immune, and this is basically it's not even connecting to those Sybil nodes. So the message propagation is staying as if nothing happens, really immune. We have the cold boot attack, which is a very interesting attack. And what we simulated here was that Sybil nodes join the network before even honest nodes join the network. And it's a very tricky attack because Sybil nodes join the network and they connect to everyone else and they form the mesh before the honest nodes connect. We see again that other protocols are very much affected, whereas Gossipsub is increasing the propagation a little bit up to 1.2 seconds, but in all cases well below the 6-second threshold. Now, what is interesting to see here is the mesh status that we have here. So here, the blue line is the honest nodes, and the orange line, the dotted line, is the attacker pairs. So we see that the mesh is formed when the Sybil nodes join the network, and then after a little while, when the honest nodes start joining the network, they form smaller meshes. We see that this attack starts just below the 1019 point in time. And we see, very interestingly, that in less than 1.5 minutes, what happens is that Gossip, through all of the array of mitigation strategies that it has, it manages to break the mesh of Sybil nodes and get basically honest nodes dominating the mesh, which is really, really important and interesting results. And Molly, I know I've run over time. I need to wrap up.
Yep. Time for us to introduce the next panel. So sorry, we can't make it.
Okay. Yeah, that was it. Sorry, I ran over time. We've got no time for questions, but post them and we'll be sure to answer them. This concludes the talk. It's a very interesting protocol. Go check it out. We have a technical report. We've got lots of things related to the performance evaluation, and it's really interesting design.